Okay, welcome everybody. We are here for another tinyML Talks. So Jenny is my co-host here. Jenny is dialing in from Amsterdam. Good afternoon, Jenny. I was going to say good morning.
Hey, thanks for having me.
Yeah, cool. So yeah, we're going to have a couple of really interesting guests today talking about data sets. And data sets are kind of like the foundational elements here for a lot of AI work. So it's really important to sort of dig into what they're doing. Some pretty cool stuff. And let's bring them on, and we'll introduce them as two students. Well, PhD candidates, students. So technically from academia, which is great. And a lot of times in tinyML Foundation, we do a lot of stuff with academia, and we have folks presenting their research. And it's a great way for people in the industry to kind of understand what's happening in academia and who's kind of trying to push the envelope. So I think that'll be a fun thing. So other than that, I don't know what else is happening, Jenny. Jenny's from Rich Impulse, by the way.
Thank you. Yeah, no, just excited to hear from Colby and Emil about what they've been doing with the Wake Vision dataset. I think maybe it's almost been a couple years since the previous datasets out of Harvard, so I'm curious to see what the upgrades are.
The upgrades, yes. First thing. All right, well, let's bring them on here, and then we'll get going. Let's see. Here's Colby. All right, and Emil. Fantastic.
Jenny, thanks for having us.
Let's get you into a proper format here. There you go. You get the big squares.
Thanks a bunch.
You're the best. So welcome, Colby and Emil. Do you guys want to give a little background, a little intro? Let us know who you are.
Sure thing. Yeah, I'm Colby. I actually just finished my PhD at Harvard, but have been focusing on tinyML research for a while with MLPerf Tiny and a variety of other sort of papers trying to lay some of the foundation for the research side of what y'all are doing in the tinyML Foundation. Yeah.
Wait, so now you're Dr. Colby Banbury?
Yeah, the degree is in the mail, I think. But
congratulations!
Yeah. That's good.
That's awesome. That's awesome. Cool. And Emil?
Yeah, I'm a current PhD student still at the Technical University of Denmark. I have about half a year left until I'm going to my defense. Then I'll also be a doctor. I did actually this research together with Colby that we're going to discuss today on an external research day that I did at Harvard. Otherwise, I've been working a bit on some data-centric methods for tinyML that maybe we can talk about another time.
For sure.
Yeah. Good. Excellent. Fantastic. And just to let folks know, this is a live stream show, Q&A. So if you're on LinkedIn or YouTube or Twitch, feel free to throw some questions in here. And we'll try not to interrupt Colby and Emil too often, but we will interrupt them. And,
that's all good.
It's your question. This is kind of like, you're going to get kind of where they're at and what they're thinking about, but also hopefully you can get your questions in there too. So sounds good. So let's talk about data sets and Wake Vision. So let me, I think there's some slides you're going to present. Colby, should I start with your version of the slides and then we'll shift it?
Other way.
Oh, start with Emil's. Okay, great. So we're going to do that. And then Jenny and I will sort of back off a little bit. We'll be monitoring the chat and let these guys kind of get into it. So here we go. Let's see. Oh, now we're in the 4-person, but we'll back off a little bit here.
All right. Well, first of all, thanks everyone for showing up to this talk and for being willing to listen to me and Colby nerding around about datasets for a little bit. As previously introduced, we're here to talk about this Wake Vision dataset that we have worked on for the majority of the last half year. And kind of take you through some of the thoughts of why we've done this and what we've even done, and also how you can use this data set in your future work. So first of all, to give you a bit of an idea of the motivation for this data set, then we felt that we have this tinyML space where we have a bunch of different applications and actually a lot of very unique applications that you don't see anywhere else in the machine learning field. But weirdly enough, we really have very few data sets that are dedicated to tinyML. And that's kind of a mismatch. And then to add on top of that, unfortunately, most of the data sets we do have, they're like either very small or like of pretty poor quality, maybe has a lot of errors in them. And that's a problem, which we'll also discuss a little bit later on. So therefore, we wanted to create like Wake Vision as a first data set that's like large scale and high quality data set for tinyML that should really be able to push the field forward and enable a lot of new high quality research. But of course, we hope that there'll be a lot of more data sets like Wake Vision coming up in the future. And because of that, we're also going to spend a bit of this talk on discussing how we are actually like scaling the creation of these high quality data sets. So I'm sure you're all familiar with this phrase that garbage in equals garbage out. It's very commonly used in machine learning, and of course means, and it often refers to that if the data that you put into your machine learning pipeline is not of high quality, then you're not going to be able to get a high quality system out in the end. And that's equally true for tinyML. And therefore, it's actually a little bit weird for us that we have for so long been stuck on working with like not so large toy-like data sets really for tinyML, because it really limits the amount of advances that we can do on like the hardware system model side in the end. So Wake Vision is also an effort to improve that and allow this next area research in tinyML. To like argument a bit further for why we need some new data sets, then we also see that data sets saturate over time. Here you have a graph that shows it for the data sets that have traditionally been used in larger machine learning. And you see that after a few years, they sort of reach human performance, and then they kind of get stuck there, and you need newer data sets to be able to create like better models and to learn from that. Okay, so let's try to get a bit more concrete. Here we, for example, have some of the current tinyML data sets taken from this MLPerf Tiny benchmark. And we've sort of like tried to illustrate the scale of these data sets. And these like bars we've created are not like completely to scale. So like just read the numbers, don't focus too much on the length of the graphs. But you can see they have around 100,000 samples. But if we try to take a look at some data sets that are like production grade or like some of the newest data sets in traditional scale machine learning, you see that they are like in the like around 10 million samples. For example, we have open images, which we'll talk a little bit more about later, at around 9 million images. And we have this common voice data set, which consists of around 24 million sound samples. And we would, of course, love to have our tinyML data set reach the same kind of scale. If we do it in a naive way, me and Colby could go out and like start taking pictures on the street, and we'd probably spend all of our PhD on just collecting around 9 million images. That would be a bit of waste of resources, so we'd like to do it in a smarter way. And I think we would also be very bored doing that at the end. But the point is, it's not very scalable, so we need to find a better way to create these data sets. What we've done for Wake Vision and what we hope can be used to create a lot more high quality data sets for tinyML is that we've actually taken this open images data set and we've used that to create Wake Vision. So I promised you we'd get back to open images, and here we are. So open images is this data set that's made by Google, where they actually just scraped a lot of images off Flickr, anything that had a permissive license, so they could use them for what they wanted. And then they ran a bunch of machine learning models and human labelers over them to create this image data set with a wide variety of labels on there. And we want to take this data set and we want to convert it into a data set that can be used in the field of tinyML. Person detection is a very intuitive task and is very popular in tinyML, so we thought that would be a good place to start. For those of you who are not very familiar with person detection, then it's a very simple binary classification problem where you get an image and then you're simply supposed to tell if there's a person in this image or not. So in the top image here, there's obviously a person. In the bottom image, you don't have a person. So to go from open images and to Wake Vision, we have this kind of extensive filtering process going on that we've given we created this little flow chart to illustrate some of the steps that we go through. So for one data sample, we first of all look if there's a person or body part present in the image. If that's not the case, like this image doesn't include a person, and we label it as such. But there's a lot of other like holes that we can fall in when creating this data set. For example, we can have images in open images that have a person very, very close to the edge of the image. And that can cause problems in our image pipeline, as we very typically crop the image before sending it to our model. So if you have these persons that are very, very close to the edge of the camera, like the edge of the image, we exclude them. We don't want to taint our data set with them. We also exclude images where the person is very far away. This is because when we work with these images in tinyML applications, they're often very, very small. Like we scale the images to like some 200 by 200 pixels. And at that point, persons that take up less than 5% of the image are basically not distinguishable, even to humans. So they will also just be noise in our data set, and we filter them away. Lastly, if we can check if the person or the body part that is in the image is a depiction. If that's the case, we label it as no person, and otherwise we finally label the image as a person. And I see, Pete, you have a question that you posted in our internal chat. Do you just want to come on and ask it already? I think you're muted right now.
There you go. So yeah, I had a question, and then we had another question that came in. So maybe this is a good chance to jump in. No, I was curious about like synthetic data. I mean, a lot of people are talking about using generative AI for synthetic data, and would that apply in this case? Like, would that help extrapolate some of the data sets that you're having? And you mentioned about kind of efficiency of creating data sets. Does generative AI help in that way, creating synthetic data for these data sets, or does that sort of kind of tarnish the quality?
It's a very interesting research question. I think if it tarnishes the quality, I think it could definitely help expand the data set. And I think if you use like some of the data we already have available, that's a good foundation for actually starting to create synthetic data, because now we have a pretty high quality data set that we can use to train a model to distinguish if there's actually a person in the image or not. And that could also be used in this synthetic data generation progress. So they can sort of build on top of each other. Yeah. What do you say, Colby?
I'd add that I think like a huge feature for this field is to use synthetic data to target like uncommon examples, or try to aim for things that are rare in the data set, but that you're worried might come up in real life. But fully synthetic data, I feel like hasn't been proven out very well for tinyML use cases, or at least in the ones that we've explored. There's probably still a lot of usefulness in just using the stuff that's already out there for the primary bulk of your training data.
Right. Yeah. Now, like for example, like I know like the kind of the original sort of Wake Vision stuff, like Pete Warden did some sort of Google Voice, Wake Word data set, which is I think more of a proof of concept than it was commercialized. But so would you consider this to be like kind of order of magnitude better quality than what we started with a few years ago, or how does this compare in terms of that?
Yeah, so this is sort of seen as like in our mind as like the spiritual successor to Visual Wake Words, which was also Google, but more Pete Warden was part of it, Akansha, Andrew Howard, those sort of folks at Google. And, it's a similar type of task on the vision side. But for both of those data sets, they were sort of quickly put out as like proof of concepts from Google that have basically like helped birth the tinyML research community. I mean, 99% of tinyML results are either on one of those two data sets. And it's sort of, we need to enter our like teenage years at this point and level up to something that's a bit more mature from a data set perspective, both like you were saying, something that reflects like actual use cases, but then also just gives researchers the tools they need in terms of like the quality, but also the size. I mean, you're really limited in what sort of things you can explore if you're working with a little bit of data, because you can't look at different data mixtures. You can't sort of start to do some of these more exotic things that are like the cutting edge of research.
There's actually a question that just came in around that. Let me put it up on the thing. So the question, sorry, Colby, you're getting your face cut off here, but traditional ML data sets comparing should usually solve harder problems. Maybe that's why tinyML data sets are smaller. You see the need for larger data sets in tinyML, which you kind of just touched on.
We'll actually get into some slides that will touch a bit more about on this question a bit later.
Okay.
So maybe you want to wait for like the full story to that. But our results definitely show that like we can create better models when we use larger data sets.
Right.
And as Colby is also hinting a bit at, these larger data sets also mean that now we can start to create like sub data sets of these larger data sets that focus on specific scenarios that you might want to train a production model to work well in.
I see. Yeah, cool. Okay, so there's that question. Another question, I think I kind of know the answer on this one, but we'll show it. Can it be legal to collect images within social networks like Facebook? Are there any legal alternatives? None of us here are lawyers or giving any advice, so. But safe to say, your data sets. Go ahead, Jenny.
No, I'm sure you both have thought about during this project the legality of things, of collecting images from the internet. So I'm curious what your experience was, what that was, even if we can't answer this specific question.
Yeah, for sure. No, I mean, it's a great point. Sorry.
Yeah, I think Colby, do you want to go?
I mean, I don't want to.
Of course, we're not lawyers or anything like that. As I said, like this open images data set that we've kind of like taken and used to create Wake Vision was created based on images from Flickr that were kind of tagged as being like free to use for whatever you wanted to.
Specifically, UI licensing. So like, there's an explicit license on the image. We make no specific guarantees that the person who uploaded the image had the legal right to give it that license, but by current machine learning standards, this is well within a comfortable legal standpoint. I think people push the boundaries much beyond where we're sitting at right now.
Yeah, I don't think we are the ones who should worry too much.
Got it. Cool. All right. Why don't we get back to the slides here, and then we'll keep going. Let's see here.
Great.
I'm going to.
All right. So let's get back into it. So we were just talking about how we took open images and we used this filtering process to take this dataset and create our Wake Vision dataset. When we do that, we end up with a dataset that's actually around 100 times larger than some of the other datasets we just mentioned in this question round, like visual wake words, and some other datasets like CFAR 100 and this Pascal VOC from 2012. These are all datasets that include a person label, but as you can see, we have significantly more images in our dataset. One thing that you might notice is that we actually have two versions of the Wake Vision dataset. We have a large version and we have a quality version. Now, why is that? I'm sure you're asking. This actually stems from the way that labels are created in OpenImages. OpenImages has a bunch of different labels, but we care about two types of them. They are image level labels and they are bounding box labels. So image level labels are what you, for example, see here in the left picture, where you have a label for a picture that says there's a person in this picture, there's a bike in this picture, and there's a tree in this picture. But it doesn't localize at all where in the image that these labels are. On the other hand, on the right side image, you have these bounding box labels that sort of draw a square around each object in the image to localize where in the image that this object is present. So the thing is that, like, for all the images in OpenImages, we have these image level labels, but we don't have bounding box labels for all the images. But bounding box labels sort of allow us to do some more advanced filtering, like checking, for example, if the person is too small, as we discussed before, or if the person is outside the crop of the image. So generally, the Wake Vision dataset that we can create based on bounding boxes will be of higher quality than what we can create based on image level labels. But the dataset we can create based on image level labels will have a lot more images in it. And that's where these two datasets stem from. The large version of Wake Vision coming from the image level labels, and the quality Wake Vision dataset coming from the bounding box images. And you can see the training set size of these datasets here as well. Maybe important to note the validation and test set that we've released from of Wake Vision is all created based on bounding boxes, and that's simply because OpenImages has bounding boxes for all evaluation sets. Now we tried to train some models on these two datasets to see, like, is it best that we have a high quality dataset or one that just has quite a lot of images in it. And as you can see from the results, like, if you just look at this kind of naively, then the Wake Vision quality dataset severely outperforms our Wake Vision large dataset. However, we can also try to combine these both and try to use the Wake Vision large dataset for some pre-training, whereas we then can fine-tune on the Wake Vision quality dataset. And this actually ends up achieving a much higher performance than using two datasets in isolation. And I think that also gives a bit more of an answer to the question we had before about, like, whether or not having a larger dataset actually helps in the case of tinyML. And here it seems like it does. So now we've kind of addressed, like, the size of the dataset. Like, we've shown that, like, we've created a dataset that's much larger than what we've seen so far in tinyML with visual wake words. But what about the quality part of it? Like, we also would like to see a high quality dataset, and how do we measure that? The primary way we've looked at it is to look at label quality, more specifically at the amount of errors that we have in the labels. So some of you guys might not know this, but in all datasets, there's going to be some labels that are simply wrong. maybe a machine learning model created this label and this machine learning model was not completely accurate, or a person created this label and, I don't know, clicked the wrong button, just didn't see there was a little face in the corner of the picture. So every data set has some amount of label error. For visual wake words, this label error rate is around 7.8%. If we look at our wake vision large, this label error rate is actually around 15%, so quite a lot higher. For a quality training set, the label error rate is around 6.8%. But we are still not completely satisfied with this. So we wanted to do a bit of relabeling, particularly for the validation and test set of open images, to see how far we can actually get this label error down. So we took the around 70,000 images that are part of our 2 evaluation sets, and we asked Scale AI labelers to go through and relabel this data set. And they got the interface that you see here on the right, where we are primarily looking at whether or not there's a person or not a person in the image, but also if the picture contains a picture in a picture / a reflection, or whether or not it's a depiction. Because as you recall earlier, if it's a depiction, we typically don't want to consider that a person. But maybe Colby will get into that a little bit later. That's a bit more of an advanced part of our data set. So by doing this, we actually reduce our label error rate all the way down to 2.2%, which we are quite proud of. And this is why we also willing to say that this is such a high quality data set. Because let me just express like how important it is to have a low error rate on our evaluation test sets. Because when you are sitting out there, you're creating models, you're creating tinyML systems, and you're testing how well they perform, having a label error rate of 7.8% on the test set, as we see with visual wake words, really mean that like you can achieve an accuracy of 92%, but above that, you're really just making errors the same way as the data set that, or the person or the machine learning model that created that data set made errors. And this is also really a limiting factor in like how good models and systems we can create in the tinyML field. So whereas with visual wake words, we could make advances that made our models up to 92% accurate, in theory at least. With wake vision, we can now make advances that can make our models up to around 98% accurate. And that's a huge difference. And with that, I'll try to hand over the slides to Colby to continue, unless we have any questions in the meantime.
Yeah, happy to just keep running through it, but please answer or ask some questions. We love the questions from the audience. But yeah, so so how was the label error calculated, estimated? It's a great question. We took samplings of at least 500 images from each data set and just manually went through ourselves. So to say like there's a label error rate would basically mean that our labels, as like researchers being very careful about how we label things, differed from the underlying labels. And so, you know, we knew what we were looking for, and like we're being very attentive, like probably more attentive than someone who has to batch label, you know, thousands of images. And sort of that's how we calculate the label error rate. You know, there's going to be some mistakes that even we make in doing that, and there are some very ambiguous things. You know, you sort of, once you get deep into labeling, you realize that like even something as binary as like, is there a person in the image or not, becomes very hard to determine. But you know, this is sort of the most accurate way that we can estimate label error rates. And so you know, with that, now that we have an understanding of like, you know, there's these varying levels of error rate in data sets, we wanted to investigate basically how that affects models of different sizes. Basically, in the tinyML domain, like, do we care about quality? Do we care about quantity and whatnot? So we actually swept a bunch of different models. These are ResNet style models from like the very, very small to, you know, reasonably large. And what we did is we looked at, we increased the error rate of the data set and then took larger and larger slices. So like the size of the data set is the x-axis of each subplot, and the error rate is sort of those different colored lines. And if we look at specifically comparing the one of the largest models and the smallest model, we can sort of make some differentiation about what you should care about at different scales. So for the very small models, it turns out that the error rate, basically the quality of the data set, matters a good bit more than the large models. So there's some literature on this in the sort of in the general research community that says that larger models basically have more parameters, and those parameters and that capacity can be used to memorize errors in the data set to ignore them. Well, we don't have that advantage in the tinyML domain. We don't have nearly enough parameters to make those memorizations. And so any error in the data set in our training set sort of takes a pretty substantial hit to the actual overall accuracy of the function that we produce. So quality matters quite a bit. But, you know, as is, you know, sort of commonly thought of, the actual data set size isn't as big of a factor for some of these small models. So we see that if we, you know, reduce the data set size for the small model, even down to like, you know, 20%, 10% of the overall data set size that we're offering, there isn't really a huge drop off in accuracy from that, like the training set size. But for the large model on the right, we do see it to start to taper as the model basically overfits to a much smaller training set. You know, this is only for when we're training and like, you know, on a single data set, as Emil mentioned before. In the sort of pre-training and fine-tuning and some distillation cases, having a lot more data matters quite a bit. But, you know, quality is primarily what you should focus on if you're looking at tinyML models. Yeah, so quality is more significant for large models. And so this is where we can make a comparison to visual wake words, the sort of prior standard for this use case. And we can see this is sort of, to explain this plot a little bit, this is where we're training in the columns. So we're either training a model on visual wake words or training it on wake vision. And we're testing on either the visual wake words test set, which is the top row, or testing on our new test set, which is the bottom row. And so we see that on both test sets, the model trained on wake vision gives a boost in accuracy, which is nice, which means that we're not just sort of shifting a domain away from visual wake words, but it's just sort of outright a better training set. You know, it gives you a performance improvement. And our test set is a good bit more challenging and sort of offers a bit more differentiation between two different models. So this is just training on wake vision quality. But if we actually do the combination, as Emil mentioned before, where we pre-train on our large set and then fine-tune on our quality set, we see a much larger improvement. So, you know, upwards of 2.2% just by swapping out the training set, which is really nice. You know, it's basically free accuracy at the same exact model, which means the same latency, the same energy consumption or whatever. And as you know, we all know, when trying to optimize these things, if you have a specific accuracy target, if you get a free 2% accuracy boost, that means you can actually have a much more efficient model if you want to trade off accuracy for latency. So, you know, this covers the high-level performance metrics, but you know, we sort of want to dig a little bit deeper. You know, we can sort of imagine a scenario where you have a model that's doing really well. You're getting 90% test accuracy, you know, based on your use case. That seems like a totally fine accuracy. But then, you know, people may have experienced this before. You then deploy the model, and the actual deployed accuracy and the deployed performance is really terrible. You know, you have this great model in you know, on your computer when you're running training and testing, and then you deploy it and it's quite bad. And that can be because of this sort of difference between the distribution of the test and the actual deployment. So if you deployed your person detection model in a dark environment, for example, it might start to perform much worse. And that's something that gets obscured when you're looking at the overall test accuracy across everything in the data set. And so what we've done is actually create a fine-grained benchmark suite. And so what that means is that we've narrowed down our validation and test sets to these sort of specific difficult instances, these sort of scenarios that tend to challenge the model. So we have gender and age. We have distance, how far the subject is from the camera and how like large, the person is in the image. Lighting, just like, is it a darkly lit image? Is it a bright image? And then depictions. This is like, is there a scarecrow in the image, for example? That doesn't count as a person, but it's a very difficult sort of challenging negative case where the model should reject a scarecrow. It should reject like a painting of a person, for example. And so these challenging instances give us a better understanding of how the model might perform in the real world if you know, for example, that the subjects are likely to be far away from the camera. So we want to really pay close attention to the far set, or you want to make sure your model's fair across all the demographics that we support. And so with this, we can get the S1 score, the actual performance on each of these subsets of our model versus a model trained on visual wake words. And you see that we sort of our model outperforms visual wake words on all of these challenging subsets, except for like a couple sort of minor ones. The sort of main one to point out would be far is where we do the worst, and that's because we sort of deprioritized far away subjects and filtered them out. But yeah, so not only is our model better in the aggregate on the test set that sort of combines all these things, but when you dig down into the more difficult examples, the models still perform better, probably because of the sort of diversity of the training set that we're working with. And this is actually very useful not only to know how your model will do in practice, but it also gives you a better understanding of how you should design your model. So let's say that you're trying to shrink your model down, make it run a little bit faster, reduce the number of operations running in your model. You might normally be looking at scaling down the model or scaling down the image size or whatever. And if you're just looking at the test accuracy, like the two look about the same. If you look at the left plot, both of these scaling methods are like pretty equivalent. But if you look at the right plot, this is when we're only looking at the far subset of one of our fine-grained benchmarks, only when the subject is very far away from the image. Well, that's when you actually realize that it's much more important to, have a larger image resolution, and you can scale down the model instead. You might pick like 224 as the image resolution and then try to scale down the model to try to get as good of accuracy as possible. And so, this is all to say that this sort of fine-grained understanding of how your model performs not only influences like when you're done, training and when you're done, when it's sufficient performance, but it also influences actual design decisions throughout the process. And so with that, we can kind of conclude and move into more discussion stuff. But, the quick conclusion is that, what we did here is we bootstrapped a data set from existing sources, that's open images. And it enables tinyML specific data sets without this enormous cost. So we didn't have to spend millions of dollars to collect a bunch of images, as Emil was saying. We can actually take, and this process is repeatable with other use cases, we can take existing resources and repurpose them for tinyML. And I think that's what we all need to strive to do right now, is improve our data resources as a tinyML community by sort of borrowing as much as we can from the traditional ML, which, there's sort of more money and more scale there already. And that, kind of gets back at the question earlier about synthetic data. It's sort of a potential avenue of doing exactly this. Another thing is that, everyone should pay extra attention to quality in the tinyML world. It seems incredibly important. I'd add that, the sort of way that we ensured quality for the test and validation set was manual labeling, which is important to have that like underlying concrete baseline, that source of truth when testing models. But now this data set is actually an excellent research platform for people that want to do automated data filtering. So for example, you can find ways to detect and eliminate errors in the training set, then train a model on your sort of new cleaned training set, and then test on our cleaned validation and test sets, and know that that accuracy actually accounts for an improvement in the model, rather than just like, if the test set was also messy, you're sort of changing too many things at once. So, this is a great platform for people to explore ways to do automated data set filtering and like quality control. And then finally, I think it's time to sort of mature the way in which we test our models in the tinyML community, understanding that performance is multifaceted and a single number doesn't necessarily tell you everything. So the sort of benchmark suite enables us to do that. And with that, I'd encourage everyone here to sort of try out the data set. You can go to wakevision.ai. You can read the paper. You can test out the data set in the collab or whatnot. It's available on Hugging-Face Datasets, TensorFlow for datasets. So it should be easy to access. And yeah, thanks everyone for listening.
Awesome. We had another question that came in. Explain the depiction case in the list of special complicated scenarios. Can you explain that a little bit?
Yeah, sorry, I sort of glossed over that a little bit, but essentially a depiction of a person is something that looks like a person but isn't. This could be a painting of a person. This could be like an animated character. This could be like a scarecrow, like I said, or a statue. It looks like a person, but if you in most use cases where you're trying to do person detection, you don't actually want it to trigger on that. Like, let's say you have lights that turn on when someone's in the room. If they have like a little painting on their wall, you don't want the lights to be on constantly. And there's other examples like that. And so this is a very difficult case for the model to reject something that is like intended to look, as close to a person as possible, but isn't. But we can do it just fine. I mean, we're, very rarely fooled by a statue or whatnot.
Right.
Paintings do happen, I think.
Yeah.
Yeah. But one thing that's maybe also important to mention is that, like, Colby, you just mentioned a use case where we definitely don't want to detect depictions, but it is entirely fair and entirely plausible that there are some use cases where we'd also like to detect depictions. So something we haven't mentioned is that you can actually go to this wakevision.ai webpage, and I believe we link straight to the GitHub repository where we store the code that we use to generate wakevision. You can change like some configuration in there to say, well, I actually want depictions to be considered persons, or I actually want persons that are smaller than 5% of the image to be included in our data set. And then you can sort of regenerate wakevision according to your configuration from open images.
Cool. A couple of more questions coming in here. Could the fine-grained benchmarks be suitable for the on-device learning research, in your opinion? Interesting to see the fine-tuning of general models to specific situations. I can cut off a little bit.
Yeah, this is a great point. So we primarily provide just for the validation and test set, just so that you understand the performance of the model in those specific scenarios. But, exactly like Emil was saying, like if you have a very specific use case, like that your model only needs to work in, dark lighting conditions, you can sort of regenerate the data set and filter the training set down to just those examples. And that kind of stuff is very useful because, like, as I mentioned before, tiny models don't really have the capacity to like learn quite as much as like these very large models that people are used to dealing with. And so narrowing the scope of the task that you're trying to do, narrowing it just to a certain lighting condition, if that is actually your deployed environment, that's a very useful thing to do. So yeah, it's maybe potentially a mechanism to enable some of that specialization.
Cool.
Definitely.
Oh, go ahead. Yeah.
No, that's it.
Another question that came in about overlap. What's the overlap potentially between the visual wake word and wake vision data sets? Will the scale of data set mitigate the impact of possible duplicate samples?
So I'm actually not sure I'm familiar with like I know visual wake words was created from this other data set. What is it called, Colby?
Microsoft Cocoa.
Microsoft Cocoa,
which actually is also derived from Flickr, I believe, although they don't specify down to the open access images. When creating Wake Vision, there was some effort by Google to not have duplicates and not have images that were sourced elsewhere, partially for licensing reasons. For example, if they find an image on Flickr that they can find elsewhere in their index, that means that it may not be like uploaded by a Flickr user. It might just be duplicated, and so they don't want to use it. So there's some filtering in that case. There might be overlap between, a decent amount of overlap between visual wake words and wake vision. But yeah, I mean, they're both just trying to do the same thing, create a person detection data set. And yeah, it's not really, you could say maybe that like there's potential leak between the test sets and our training set, maybe.
Or the other way around, really.
Or the other way around, our test set and their training set, there's some leak.
But anyway, I think we can say that like if there's overlap, like it would maximum be like in the like low single-digit percentages. So I think
it would probably be very little, yeah. And I'd also say that the fact that we perform better on our test set and their test set sort of means that like if there is some leakage, like there's certainly not leakage between our training set and our test set. So
Got it. Okay.
Yeah, there's only so much, I guess, to control.
I have another question here. Jenny, feel free to jump in if you have any questions of your own. I have another question here. Here's a kind of a non-data set question. Just how did you guys get together to work on this? I mean, you got Copenhagen, Cambridge. Like, what's the connection?
I guess that's a you question, Emil.
That's a me question, perhaps. Yeah.
I think I got lucky.
Yeah, I think that's Vijay you're gonna have to ask there. I reached out to their lab quite early in my PhD just because like Colby and Vijay and all the rest of the Harvard Edge lab has been doing a ton of interesting stuff in the tinyML field, and I thought that the direction they were going in was kind of the same as what I wanted to do, like work a little bit more with the data side of tinyML, which I think is unfortunately often a bit neglected. So I reached out to them and like we discussed a little bit about the different projects we could do, and then I got paired up with Colby to work on this wake vision idea, which I'm of course also very happy about. It was a great stay there, so I can only recommend people to try to reach out if you're interested in a similar experience.
Right.
I'd add that Emil was an excellent collaborator, and that was really awesome. And one of the nice things about the tinyML community is like a research subject is that it is like pretty small still at this point. It's definitely grown a lot in the 5 years that I've been working on it, but it's still small enough that like most of the interesting papers that come across my thing, I'm like, oh, like I know those people, like I've talked to them before, or, like like Jenny and I have worked on stuff before together and everything. So
Indeed.
It's nice. Everyone is familiar with everyone's name at some point. So
Right.
Yeah, we are definitely a small community. So a simple email could change your life in that regard. So send me an email.
Yeah. What can go wrong?
That's right. I would also encourage folks, we have a Discord server that's growing in size, and there's some interesting conversations on there too. And so people who are listening want to kind of join in on a conversation and maybe don't know who to email, they could join the Discord server and post a question out there too. And hopefully someone here will answer that. Good. Yeah. So let's see. I don't think we have any more questions from the please link the Discord.
Well, maybe I could just ask a quick, maybe you could answer really quickly. What's next?
For us or for the talks here?
Yeah, you moved up, right?
Yeah.
Next data set. Wait on what?
Yeah, I mean, first I'll sort of, plug the Harvard lab. There's still going to be a lot of work coming out of, even though I've graduated, there's still going to be a lot of work coming out of Vijay's Edge Computing Lab at Harvard, including extensions to this work that are already sort of ready to go. I think there's, partnerships that we're working out with the tinyML Foundation on getting this to be a useful resource for folks in the community and like a more standard benchmark for research to be done on. For myself personally, I'm starting at Microsoft in a couple weeks. So yeah, working on similar stuff, which I'm excited about.
Yeah. As we talked about, like in the conclusions, I think some future work that we suggested from this and that the Harvard Edge Computing Lab might very well continue on is like we wanted this process of creating Wake Vision to be very scalable, but we still ended up for Wake Vision employing a lot of people to do manual data label cleaning, and that's not necessarily the most scalable thing since it costs a bunch of money. So trying to use our dataset actually to do research on automatic ways to clean these labels would be a really good idea. I know some things we've talked about previously was also that, like, this dataset and most datasets we use in the academic community are static. Like, you can't add images to them very easily over time. Whereas if you go to Google, I'm sure that, like, they don't have a static data set to train their image models. They, like, gather them on the fly. So that could be a research direction as well. For me, as I said, I'm like very late in my PhD. I'm probably ending up in around half year. I'm not exactly sure what where I'm going to be jumping next, but I'm at least having like one project left on tinyML that's likely going to be a bit more in the direction of doing neural architecture search with, like, considering data as a part of that as well.
Awesome. Well, congratulations, you guys, on your PhDs, and Colby, good luck at Microsoft, and Emil, thank you for joining us, and good luck with the rest of your journey, and thanks for the amazing talk today. And please join us on the Discord.
Oh, yeah.
For sure. Thanks for having us.
Awesome. All right. Thanks, everybody. Take care.
Bye.